All right, so what I want to do today, I'm going to kind of scroll through these notes at the beginning. We're going to finish these notes really quick, and then the notes check I have for 9.1 is super easy. So we're going to do that one just to get you some like free 5 points. And then we'll start Taylor's series. One thing we're going to kind of the goal for today is to avoid having to do this ever again. So we really want to find a better way to write a Taylor polynomial and soon a Taylor series. We'll explain the difference between those in a second, where I don't just have to take derivatives forever and ever. So we're going to be trying to do a bunch of different things to that. I remember when we were working with Taylor polynomials before, we were trying to match each derivative to the function that we're creating. So we kind of have our point, our first derivative with x to the first power, second derivative, 2 factorial, x to the second power. So we're kind of matching powers, factorials, and the number of the derivative. So let's try to just use that formula again. I'm on the very back page. We are going to write a third degree Taylor polynomial about x equals 3. That's all weird verbiage. Can you tell me anything you learned from those directions? All right, the center is 3. What a lovely idea. Oh, good. Center is 3, and the third degree means I'm going to end with a cubed as my last term. All right, so I'm going to call this p sub 3 just because it's a polynomial of degree 3, and x is the letter we're using, the variable. All right, does anyone know what the first term of our Taylor polynomial is going to be? -4, full stop. That one's always just a constant for us when we're creating these. All right, let's roll a little bit harder. What's the second term of this series? All right, 2, and what else? X minus what number? 3, our center. Perfect. All right, the next term, what's that going to look like? All right, we got 7 over 2 factorial. So our factorials start at 2. You can start them at 0 if you want, just for the pattern. Were you not here this first day, Nate? No idea. Cool. All right, we're just plugging into this formula right here. So we're using a formula from the very top. Wow, that was a long scroll. So I'm using that formula at the very top. You're noticing x minus the centers in all of them, and then the number derivative matches that number factorial. Yeah, I would definitely watch the video for an explanation of why that formula is the way it is. Oh, nice. And then you left. Also, this video up here, we watched a couple minutes of this before I started the video in class. The whole thing's like 20 minutes long. It's a really good video if you want. It's linked on there and in our Schoology page. All right, what comes after this 7 over 2 factorial? X minus 3 squared. All right, last term that we have to write. All right, a reminder, are we going to simplify this? Heck no. One reason, we really want to be able to see the x minus the centers. It's kind of the whole point of this thing, is to be able to see the center of this series. So there's no way I'm going to multiply all of this out. And then the only thing we could really do is call 2 factorial 2 and 3 factorial 6, but why? So there we go. Now what we're going to do is this is a good preview into what we're doing today. So if we now are going to take this function that we made, this was for f of x, and I want to use this to write a 4th degree Taylor polynomial for g of x, which I'm calling f of x squared plus 3. And I want to do that about x equals 0. What's the center going to be of this new one? What else could I call it besides a Taylor polynomial then? A Maclaurin polynomial, that fancy Scottish mathematician instead of Brooke Taylor. And then 4th degree, what does that mean? Yeah, we're going to have something to the 4th power. Now, this seems a little weird, and it also seems like something I don't really want to do by taking 4 derivatives. if you think about this function right here, the first derivative of that would definitely have a chain rule. So I'd be multiplying by 2x for the inside. And then after that, because I'm multiplying by that 2x, the second derivative would have a product rule with another chain rule. That derivative is going to get way nasty, way fast. So I don't really want to do that. I want to be a bit more clever. Well, what does it look like? This is a very vague question. I'm hoping for a specific answer. What does it look like we did to f of x here? Very vague question. All right. Let me try to ask a more specific question. What's in place of where x was? X squared plus 3, right? So it looks like I took x squared plus 3 and I substituted it where x is. Would you agree with that? All right. Well, this thing's a polynomial. I can substitute into polynomials. So let's try that. So my goal for a second is I'm going to take this thing, and everywhere there's an x, I'm going to try to write x squared plus 3. And I'm going to see if it works. So I'm taking this, transforming it into this. This is one of the things we're going to be able to do today. So let's start with -4. Are there any x's to plug into with -4? No, so he's just going to stay the same. The next one, instead of x, I'm going to write, not that thick, x squared plus 3. I'll keep the -3, close parentheses. Is anyone getting a little excited about what we're doing? Partially because of that +3 -3. What are those 3's going to do? They're going to cancel. What was my center of this new one supposed to be? 0. So if I just have 2x squared, this has now changed the center to be 0 because we won't have like x minus the center. We'll just have x minus 0. All right, the next term, I'm going to have plus 7 over 2 factorial. Here, again, I'm going to keep writing down x squared plus 3 minus 3. I'll simplify that in a second, squared. Should I keep going? Someone said no, and you actually could be right. Yeah, x squared squared will give us a 4th degree Taylor already. Just for the sake of argument, I'm just going to plug in so we can just see this happen one more time, but we don't need this one. 5 over 3 factorial. We could keep going, but we won't need this term. So here, what if I kept all of this? What degree polynomial would this one be? Careful. 6th degree. So it depends on how I ask the question. This one is not needed because we only need the 4th degree. So I'm just going to simplify those 3's out. So I have -4 plus 2x squared plus 7 over 2 factorial x to the 4th. And that would be my answer. When I have like x squared times x cubed, so same base multiplying.
Oh, it's different power.
So you're thinking this guy there. All right. So we're going to start playing more with this idea. Yeah, Emery. That's a great question. So probably kind of like when I give you an integral that's going to work out with USUB, you're going to get a problem that would work out. We'll look at kind of less specifically working out questions today, where we plug in, and most of the time, honestly, we'll be working with Maclaurin series, so kind of the centers are all going to stay the same. But if you got something as specific as this, it would be created to work out. All right, so what I want to do is give you a second to do a 2-question notes check. The first question looks just like this one. Everyone in the room can do this because you have the formula at your front page. I just want you to plug it in, just stop. Then the second question is going to ask you for a coefficient of one of your terms. I would look specifically at this question. It looks very much like the one on the notes check. So for example, if I wanted to find the coefficient of the 3rd degree term, remember that's the 3rd derivative over 3 factorial, making sure you're plugging in your center for your x value in that derivative. Those are the only two questions on the notes check. So I just want to get some practice with this formula before we start manipulating some new ones. So I'm going to pass out a notes check. The versions are all very, very similar. So even if you're working with a neighbor and they have a different version, you should be able to. I'm going to put a goal of about 7 minutes to do this notes check. I think that should be enough time. We don't have a notes check at the end of today. So this is an order matter. Yeah. Yeah.
How can we only use the one at 2?
Because I am centered at 2.
Oh, okay.
So they're always going to tell you a center that you're going to use. Yeah. All right. So I'm going to put my goal up for 7 minutes. So the first one's very much like the first question we did on the very back page. Or like the one we did on the front page where you're just plugging in the derivative. Yeah. Yeah. For me,
Zero over it. Still zero.
just of x. So you're functioning like your s is n.
Wait, so what I just rate S and X?
I would just write p so and then p dot.
Oh,
Wait, do I have to write the X too? Or no?
that's what you do.
I would like it's like you're writing f.
Oh, and then I do this. Okay. Oh, okay. Negative.
Over.
For me, it's
Yeah.
If I have a 0, then technically I go.
Sorry, I'm laughing because everyone's
Oh,
trying to ask the same question.
Oh, yeah, so if I have a 0, I don't have to get that whole like extra. Do I have to do this? Do I have to start?
What do you do? Special.
Theoretically, there is a 0 factorial and a 1 factorial. Both of those are equal to 1, so that's why they're not writing it.
Oh, okay.
But if you wanted to, you could just let's see.
Okay, thank you.
What is the second?
So it's like this one for the coefficient. So you remember your coefficient is your whatever derivative over that factorial. So what degree are you looking for?
5. 3.
3. So I would go ahead and take 3 derivatives, plug in your center.
Oh, I actually.
Yeah. Unless you know the Maclaurin series or the.
But what is your control bar?
So,
Wait, you look it up? We fit it. Oh, we fit it. Good math, whatever you want to do.
So on that, we get the order. So we get the 6 for those 2 words. Not like the plus the first script. And then where does the X line?
so once this is like
Joking.
like a tangent line where you're doing x minus the x value where you did it. So there's always going to be this afterwards to represent like your variable and your center. So
That just comes from the 2 being the center.
the 2 being the center. Yep. So this X minus whatever is always gonna be here. The reason it's not in the first one is it would be to like a 0 power.
Is there a problem with this? Oh, you just don't want to get
Okay, and then the next part, the 9.
You just need, it's like the coefficient one that we did. So
Is it always start with respect to word? Does it always start with 1? Yeah, what's up? You just keep going. Yeah.
So this
problem.
Yeah.
How to fit X.
So I want the third degree term, the cubed term, I want both.
I don't do it then.
You don't have to write the whole thing, like, seriously, like, I don't want
Just
it.
the,
Just the coefficient.
You guys-
and the third.
just the code. You don't need to write it there.
So not the X
The,
What? Alright, so look here. So
The 20.
notice the X cubed for the third degree term. So I'm essentially asking for this thing right here.
yeah.
That thing is from the third derivative with our center plugged in over 3 factorial. I know you, Nate Griffin, know how to take 3 derivatives. Just plug in a number and put it over here. What you're gonna do. Three derivatives.
I don't, do I keep the?
No, no, both of them just the starting Probably.
That's how I use it.
Oh.
And then how do I?
Oh,
that's the binding.
Okay, so you're trying to find the coefficient of the like third degree term. So like this, that's coming from your third derivative over 3 factorial with your center plugged in. So can you take 3 derivatives, plug in your
Wait,
center?
I thought you don't need the fact, you need the factorial for this.
We're not gonna finish number 2 today.
You don't need the fact, oh, those factorials.
I like that.
The top on the first group.
There's so many things on the notes that I haven't done.
What?
No, so what we're gonna do probably is one of the days, I think there's 994 and 95 is that right?
Where?
For everything, I think what we're gonna do is I'm just gonna finish my order and then that's okay. So it'll technically be an extra day is what I plan for the unit, but I don't. That's it. Just that. And then don't need any. I don't like these 5. You have 2x. Oh, what should they be?
And then if
Just the thing. No, I actually would just write the number. Yeah.
4 now for all these.
We actually just need the third. So you don't need to mess with any of the other ones. So really, you can do this. All right, as you guys are finishing up, you can drop them on, yeah, that's it. As you guys are finishing up, you can drop those on the middle table or switch them out for me as I bring around some unit notes. We're gonna do a little bit of these and then stay with you. Hi, there should be an X. We need to work on
John, I don't.
Why do you guys always want to go less exact? Yeah. It's been exciting. I
I'm debating if I should teach myself the entire unit tonight, study through them, and then learn it when I go for it and take the test, or if I should ask myself. I'm low-key like, I just absolutely grind. I honestly, but I don't want to any other scenario. I would have to only. I also think at this point, it can't be another time. Yeah, another one. So I'm like, maybe I should just like freaking physics so that I could learn the entire unit in 1 minute. It's okay, last. Yeah. Yeah.
All right. Are we ready to rumble? Ew. Someone in the hallway was like, "Hey, do you want this?" and gave me trash, and I took it. I think he was doing it as a joke, and I was like, "Why did I take this?"
I know. I told him not to put all this.
All right. So I would love to do the first page of. It's going to take a little bit of time, and then we're going to take a break. So let's get going. Eventually, we are going to have 3 elementary Taylor series that we will have memorized. So we're going to find those 3 right now so that we can do kind of like what we just did on the last one, where we can substitute to it, where we can add stuff together. We're going to have lots of things that we can do because polynomials are easy to work with, even if they are infinitely long. So let's go ahead and we're going to find the Maclaurin series for e to the x. When I say the word Maclaurin, what does that make you think of? The center is 0. And for the most part, we're going to be working with a lot of series where the center is 0 for the sake of just kind of using a simpler series. Also, they're just more helpful. So let's start with e to the x because it's the easiest one. Someone's angry. All right, what is the first derivative of e to the x? E to the x? Okay, cool. What about the second derivative? All right, I'm trying to find a pattern. I don't know if I see one. The third derivative? Okay, I think I get it now. Are they all just e to the x? Wow. All right, what number should I plug into all of them to get my coefficients? 0, my center. What's e to the 0? 1. I mean, no, but I'm being really aggressive.
I mean, like, if you're like doing work on a test, you have to like solve.
If you're doing work on a test, you're gonna have this one memorized. Like I told you. You could build it if you needed to, but this one's really not hard to memorize. All right, so what is the first term of this series? 1. What is the next term of this series? 1 times x minus 0. So I'm going to simplify all that to x. Wow. All right, what's the next term? Yeah, eventually. It's not going to be hard. All right, over 2 factorial. X squared. Now I'm going to write it x squared over 2 factorial just to be nicer. I think it looks pretty. That's how textbooks write it. All right, I'm going to do one more, and I think we're going to get the pattern. All right, what do you think the next term would be? Okay, I'm going to write what's called the general term. Think of that as like your nth term for your series. It's just the term with n in it, so I could plug in whatever number term I wanted. What would the general term be? Now, notice at the end here, I have written plus ... So in the notes we were doing before that were called Taylor polynomials, the purpose of those was to approximate something. So we used a finite number of terms. You guys might have used 3 terms or 4 terms on your notes check, depending on what degree I asked for. we are now going to be using infinitely many terms, which means literally all of the derivatives from the first derivative all the way out to the infinitieth derivative will match, which means we don't take these with enough seriousness, but means this series actually equals e to the x. So if I was able to graph all infinitely many terms of that polynomial function and able to graph e to the x at the same time, they would be the same graph. So these guys are equal. If you're thinking about interval of convergence, where they are equal for everything, literally all of the numbers that I could plug in for x, these two will converge. They will be the same thing. That's pretty darn powerful. E to the x is not something that's easy to plug into, easy to work with. Though we have infinitely many terms, we now have a really nice polynomial function that's equal to this transcendental function. So a really cool idea. Notice it's not hard to memorize, though. You've just got x to whatever power over whatever factorial. This is the way we're going to write most of our series today and moving forward, where we have 4 non-zero terms and our general term separated with that kind of ... notation. Yeah. What do you mean? Yeah, so technically we usually start these at like n equals 0, just for customary reasons. So this could be over 0 factorial. That's 1 by definition. And this one could be over 1 factorial. If you want to add those, you're not wrong. Just generally they aren't good. Yep, exactly. So if you want to add that stuff in, that's totally fine. Now, you're going to notice today I'm not using a ton of sigma notation, unlike what we did last. That's because when we start manipulating these series, this index that's usually at the bottom, so this is how I would write this in sigma notation. Generally, do this, but when we start doing things like taking derivatives or taking integrals, this can get kind of slightly off, which is a little bit annoying. So generally, to get all my points on the AP test as well, because they usually ask for the first 4 non-zero terms in the general term, super easy to just kind of write out the way I wrote it out over there. All right, let's try sine of x. What's the derivative of sine of x? Cool, cool, cool. What's the derivative of cosine? Yeah, eventually it cycles, right? Why do I do that? Why do I act like I don't know what's going on? Is it annoying to anyone else? Sometimes I annoy myself. Ooh, Oscar-worthy performance. What's the derivative of negative sine x? Negative cosine x. Now, Rashad was saying this cycles. He is completely right, because what's the derivative of negative cosine x? Positive sine x. All right, what value will I be plugging in for my center? 0. How do you know? Maclaurin. Imagine your name was Taylor and someone cooler named Maclaurin came along. I need to show you guys a picture of Brooke Taylor. He has her L'Hopital's wig. His is stupid compared to L'Hopital's wig. Stupid in a bad way. It doesn't look very good. All right. What's sine of 0? Yeah. All right, save it, because what's cosine of 0? What's negative sine of 0? 0. What's negative cosine of 0? Negative 1. All right, so as I write this down, I don't know if you heard me say the word before, but we're going to be writing the first 4 non-zero terms. So like on your notes check, you had a term that kind of went away. It was 0. Some of you guys wrote it down, but really when we write down these series, we want to be able to plug in n equals 1, get the kind of first, or n equals 0. Plug and get the first non-zero term. N equals 1, plug in, get the next non-zero term. So will I be writing down a constant term, one without any x's in this series? No, because my f of 0 is 0. I'm going to skip that one. So I'm going to go now to this guy. This is now our first degree term. I have 1 times x minus 0 to the first power. So I'm just going to write x. Will there be an x squared term? Will there be an x term?
Yeah.
What will it look like? Three factorial. Perfect. All right, now, will there be an x to the fourth term? No, because the fourth derivative is going to be at back up where f of x is. Will there be a fifth degree term?
Yeah.
What will it look like? All right. Will there be a sixth degree term? Will there be a seventh? What do you think it looks like? All right. I'm going to write plus ... What do you, this super vague question, hoping you're reading my brain. What do you notice about these terms? Letter A. They alternate. Perfect. Does anyone remember what our alternators could look like if we were writing a series? What does alternator look like? All right. I want to know, should I use, if I want this one to be my 0th term, starting at n equals 0, should this be -1 to the n or -1 to the n plus 1? What do you guys think? If it starts at 0, do I want it to be n or n plus 1? All right, if it's n plus 1, 0 plus 1, you don't have to come in. I don't know. Is that wrong?
N plus 2.
Why would you do n plus 2? If you start at 0, what's -1 to the first power? -1. Do I want it to be -1? No. I could do n plus 2, but that's silly. Let's just do n. All right. So we're going to have regular alternator. Now, I need a way to plug in 0 and get 1, to plug in 1 and get 3, plug in 2 and get 5, plug in 3 and get 7. Let me repeat that and write some stuff down. So this is going to be my n equals 1. This is going to be n equals 2. This is going to be n equals 3. So I want to find a exponent, a factorial where I can do that. Do you have an idea? 2n plus 1, is that going to work? You'd be remembering this kind of from, I'm going to move my 4, sorry. We had a similar looking exponent on one of our alternators in our interval of convergence notes. That was like always -1 because it always came out to be an odd number. It's a really good way to define odd numbers. So if So kind of just testing out some stuff. A good way to find the exponents go up by 2 every time. So think like a slope of 2. So the 2n, and then to adjust to get 1 on our first term, we would need the 2n plus 1 to get the first degree term there. All right. This again is true for all x values, -infinity up to infinity. So these guys are equal to each other. Now, this series isn't super scary. There's a lot of patterns, right? What do you notice about all the powers and all the factorials? They're all odd and they all match each other. So just like the E one, all the powers and factorials match each other. Not too bad. Any predictions on cosine? You think it's going to be the even ones? All right, I'm tired of taking derivatives like this, though. You guys want a new way to do this? All right, super vague, hoping for a specific answer. What calculus way can you think of to go from sine to cosine? I could integrate, but then I'd end up with a negative sign. What else could I do? From sine to cosine. What's the opposite of? Yeah, I could take a derivative, right? Is the derivative of sine cosine? All right. So, well, if I could take a derivative on this side, I could take a derivative of infinitely many terms. Let's do it. It's actually not that hard. So let's talk. Derivative. Once we do this, we get to take a break. Be more motivated. All right. So we're claiming cosine is the derivative of sine. Now, Taylor series are made brilliantly for manipulating these series like this because it's built for bravery. We get to start with the easy term and then get to the hard term. So we're building our confidence. What I mean by that, we're going to start with the first term, x. What is the derivative of x? How great did that feel? Wow. All right, the minus is going to stay. I'm going to keep the 3 factorial. I'm going to simplify in a second. What's the derivative of x cubed? Perfect. All right, I'm going to keep the factorial for a second. Derivative of x to the 5th. Don't you feel brilliant? You're doing Taylor series right now. All right, what's the derivative of x to the 7th? All right, here's where it starts to get a little weird. Again, we are not in multivariable calculus. So we have multiple variables in our term, but only one is going to function like a variable for this derivative. What variable am I taking this derivative with respect to? X. So when I look at that term, the only thing that's a variable is this x. This is a numerical power. That's a numerical denominator. -1 to the n. That's a number as well. So the things that are going to stay, the alternator, not going to change. The denominator, not going to change right now. The only thing that does change is that numerator. X to the 2n plus 1. What's the derivative? X to the, you said 2n. How am I getting that 2n? I'm subtracting 1, right? All right, I'd like to clean this up a little bit. 1's feeling fine. Actually, let's just go straight down to here. Just like your normal derivative. So this 6 is like 7 minus 1. All right. So let's think about what's going to cancel here. What 3 factorial? What is 3 factorial? Could you list out the numbers for me? 3 times 2 times 1. So would you agree with me the 3's would cancel here? All right, so I'd be left with 1 minus x squared over 2 or 2 times. I'm just going to write 2 factorial. A lot of these have had factorials in them. All right, what's 5 factorial? Yeah, which is 120. All right, the 5's would cancel. What is this term going to look like now? F to the 4th over 24, which I could write as 4 factorial. I've got 4 times 3 times 2 times 1. All right, I don't think I even need to write the next one out. I think you can predict what it is. What do you think? Perfect, x to the 6 over 6 factorial. All right, now that we've built up our bravery, let's look at the last term. All right, alternator gonna stay just as is. When we normally break this factorial down, we normally do 2n plus 1. And what would the next thing be if we're kind of breaking down? 2n factorial, right? You have 2n, 2n minus 1, 2n minus 2, all the way down to 1. I think these guys are going to cancel. So what's going to be left? X to the 2n and 2n factorial. All right, you know what 2n is going to do every time? It's going to make an even number, just like what you guys predicted. This, again, is for all numbers. Those two are equal to each other. Very powerful stuff. Yeah. Not really, because they don't have any x's in them, so they're kind of just following along as like a fancy way to write a constant, really. So they're just rolling around like coefficients. Cool. All right, so when we get to the Unit 9 test, we are going to have these memorized because we are going to build off of these series instead of just taking a bunch of derivatives and hoping we see a pattern. So when we come back, we're going to try to do the rest of this, or at least a couple of things on this front page. We're going to try to plug into some series, take a derivative of a series, play around with that. Let's take a solid 5-minute break. And when we come back, we will finish as much as we can. I can't remember how much of this I did in my other class. Oh, I only did the first 2. Kind of.
Yeah. I'll figure it out. I'm sorry. It's all right. It's okay.
Wait, what? Like, you saw me?
Oh no, I saw the picture of like you in the voice. Like you pointed at Danny. He was like, and I was like, no, it's actually the other guy. He's like, oh, I didn't know that, brother. Oh my god.
Wait, for what?
I saw that, but I didn't know what it was.
Wait, so yeah, this
I didn't see it. I saw it.
No, I didn't see pictures. This is my friend. They got black hair.
Your friends in the. That's Avery too, actually, huh?
What's Aaron's friend?
Hair?
My keyboard.
Well, how's that racist?
Wait, what's black?
The Chateau Noir.
I know what.
How's that?
Yeah, weird, like,
Yeah, yeah.
Womp.
I just Chateau Noir. W-A, and they just try it for you. Huh? Eh,
This one's got weird.
Should have done our break earlier today. Poor decision on my.
Watch yourself.
I have
Looking up really It is. From Louis.
Oh, that one so good. I get that every time I go there.
Right now.
Jealous.
That big half the class board. With an ocean of half test, half business. It makes
I
me
saw
sick.
that on the menu. I was like, really? It's all delicious. It's the best cafe I've ever eaten. No, I don't know, but in my heart. I don't know. They have like grill it, and then it has like cheese on it, but it's like not pepperoni. Yeah, probably, but it's so good. One time I never. When I was in my drawing class,
All right. I actually kind of only want to do like the first couple of questions here so that we don't rush anything. We'll do a little bit of schedule talk at the end, kind of give you an overview of what our class looks like until we get to the AP test. So these are the things we're kind of allowed to do to a power series, Taylor series, whatever you want to call it for right now. We saw substituting into the series. That was what I did with that x squared plus 3 right at the end of the 9.1 notes. So we're going to do that a lot. We can multiply or divide series. That can be either really easy or really hard, depending on what we're multiplying or dividing. If you're doing a constant or a variable, that's going to look a lot like distributing. That'll feel really easy. But I could theoretically multiply two series together or divide two series, which then looks like an infinitely large FOIL or an infinitely large long divide. That gets a little bit harder. So we'll save those kind of for next time. We could add or subtract two series together. Think of that kind of like combining like terms. And then kind of like we just saw, and we're going to see again, we can take the derivative or integrate a series. So I kind of just want to give you an outline of how you would start a question like this, how you would format it. And then we'll just take a look at the schedule. We'll continue with these next time. It'll probably be a good thing that we get a little bit of a brain break in between starting and finishing these notes. So here's how I would attack these questions. The first thing you're going to need to identify is which series we're going to try to build off of. And again, you kind of have your first three. You have sine, you have cosine, you have e. For this one, I would argue you want to use sine. Does everyone agree? All right. What does it look like I've done to change sine of x into this one? I substituted x squared where x was. So I'm going to do that in a second. Notice the directions here. These are the ones you see pretty much every single time on the Taylor series free response. I say the Taylor series free response because you're almost guaranteed one. It's almost always number 6, which means it's the last question you're ever going to do for calculus, which is fun. The directions are give the first 4 non-zero terms in the general term. So that's why I was writing the series like this every time, because that's the directions they give you on the AP test. Not only is it easier, it's going to make sure we get our points. So the first thing I like to do is I like to take sine of x and I like to just write it down, because on my test, on the AP test, they're not going to tell you what that series is. So we want to get that guy down on paper. So was that the even or the odd one? The odd. So we start with an x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus, leave some space, dot, dot, dot. And then our general term. We had our alternator. And the way we wrote odd numbers was that 2n plus 1 that Griffin gave us. Now, we do really, really need this plus dot, dot, dot on the end. I'm not being a stickler when I say that plus dot, dot, dot. We need it because we're claiming that these two are equal to each other. If we leave that plus dot, dot, dot out, we are now creating linkage issues. So I will be mean about that plus dot, dot, dot at the end. All right, so once I have this written down, really all I'm doing is I am going to plug in x squared everywhere there's an x. Now, you cannot simplify it at all if you really don't want to. I'm going to simplify it a little bit because we're going to use our answer here. So for my first term, instead of x, what's it going to look like? X squared. You're brilliant. Wow. Again, I think these are great for bravery building. Next term, a little bit harder. We've got now x squared is going in where x is, and then we're cubing it. So x squared cubed. Good. My other class said x to the 5th, and they were so silly. Is the 3 factorial going to change? No, there's no x's in that. All right, what's the next term going to look like? X to the 10th over 5 factorial. All right, what else? All right, Now, with the general term, you can do it algebraically, or you can try to kind of come up with your own formula. I'm going to try to just do it algebraically. So the alternator, no x's in it, doesn't change. The factorial, I noticed they weren't changing on the bottom before. I don't think they're going to change now. I know there's going to be an x. I just have to figure out what power it is. So I'm doing x squared to the 2n plus 1. How could I simplify that exponent? How did we get to 6 from 2 and 3? Yeah, we multiply them together. So 2 times 2n is 4n. 2 times 1, 2. Now, I would argue that none of the steps we just did were horrific, right? They weren't super terrible. I'd take this any day over trying to rotate a region around a line. The biggest thing here is you got to be willing to write it down. I know that a lot of people don't like to write a lot of steps, but writing it down and taking it piece by piece will make these questions a lot easier. So speaking of writing it down, taking it piece by piece, what is the next one asking me to do? Take a derivative. So I'm going to take it piece by piece. This is f of x. Let's find f prime of x. Again, let's build our bravery. The first thing we have to take the derivative of is x squared. 2x. I'm pretty sure I could teach my Algebra 1. I have taught my Algebra 1 students to do that. All right. I teach them power rules sometimes when I'm bored. All right. I'm not going to simplify anything because this is the last question that deals with f of x. So I'm just going to keep the factorials along the bottom and take the derivative on the top. What is the derivative of x to the 6? All right. Going to keep the 5 factorial. What's my numerator? Keeping the 7 factorial. What's my numerator? 14x to the 13th. Wow. Yeah, we have to do the general term too. So is the alternator going to change? Is the denominator going to change? Liar. No. Sorry. All right. The x's are going to change. Oh, right now? Oh. Right now? So unlucky, man. Oh, and it even froze. Ah. Oh, no.